Hello, my name is Rakesh Ravi, and this is my Physics 2212 Lab 4 report on the bar magnets. So the goal of this experiment was to measure how the magnetic field strength of a bar magnet changes with distance and compare my results to the theoretical dipole model. So this is how we did that. So we modeled a bar magnet as a magnetic dipole. Its field follows the power law B equals K times R to the N, where N should be about -3 for a perfect dipole. Taking the natural log of both sides gives ln of B equals ln of K plus n ln of R. So a plot of ln of B versus R versus ln of R produces a straight line whose slope is n. In vector form, the field is V equals mu naught over 4r pi cubed times 3 times mu times r hat minus mu, which is the equation I use later in my glow script model. Okay, so here's the experiment setup. To start, we rotated our phone until the x component of the magnetometer read about zero. This alignment made the magnet's field orthogonal to the Earth's magnetic field, minimizing interference. I then found the exact location of the phone's magnetometer sensor using the tape cross method. These steps ensured that each measurement used the same geometry and orientation for consistency. All right, and here's the data we got from the lab. So we measured the x component of the magnetic field for five target magnitudes, and we got 20, 70, 120, 170, and 220. And the corresponding average distances were roughly amounted to 0.29 meters, 0.19 meters, 0.16 meters, 0.14 meters, and 0.12 meters. As expected, the closer the magnet was to the sensor, the stronger the field became. All right, and here's the graph that was plotted from this. So when we plotted ln of bx versus r versus ln of r, the data formed an almost perfectly straight line. The best fit equation was -2.8x minus 14.23, um, giving an exponential exponent of n equals -2.8. This is very close to theoretical -3, confirming that the magnet behaves like a dipole. The intercept -14.23 corresponds to ln of k equals -14.23, which was used to estimate the magnetic moment. Okay, and here's the GlowScript computational model. So we use GlowScript to visualize the dipole field. And using the relationship between K and mu, the magnetic moment came out to about 3.29 am squared. In the simulation, orange arrows show the on-axis field, and the cyan arrows show the perpendicular field, and the magenta arrows represent the 45-degree measurement. The simulated field at 45 degrees was 3.47 times 10 to negative 5 T, compared to my measured average of 4.24 times 10 to negative 5 T, an 18% difference, which is very reasonable for a phone magnetometer. Okay, but here's where we could have gone errors. This model assumes the magnet behaves as a point dipole and that Earth's field is fully compensated. Possible errors include slight misalignment with magnetic north, near field effects from the finite magnet length, and small sensor placement errors. Nearby electronics could have also added excess magnetic fields to the system. All right, and here's a discussion. If I connected two identical magnets end to end, um, Um, wait, no. So the first what um, if the meter scope was laid out at an intermediate angle, the measured BX values would include a constant component from Earth's field. Um, that would shift my LN graph, with changing the intercept and making the slope deviate from -3 because the readings would no longer represent just the magnetic field. For the second discussion question, what if we had stuck two magnets end to end and ran the experiment? Well, if I connected two identical magnets end to end, their dipoles would add together, which would effectively double mu. The magnetic field at each distance would roughly double, so the ln graph slope would stay the same, but the intercept would increase, which would shift the line upwards. Okay. And to conclude, overall, my experimental slope of -2.8 closely matches the theoretical -3. The simulation and real measurements of 45 degrees agreed with 18% error. This shows that a simple magnetic dipole model accurately describes the field of a small bar magnet when the setup is aligned properly and environmental fields are minimized. And thank you for watching.